Hello, this is video 155 on Financial Math for Actuarial Exam 2. We're continuing with duration, Macaulay duration, and in particular Macaulay duration of bonds in this video. This is going to be a pretty long and theoretical video, but it's got a lot of practical importance, subtle practical importance that you wouldn't know unless you hear what I'm telling you in this video. Okay, it's not something you would expect ultimately, and it really can give you a financial advantage if you're doing a lot of investing in bonds, to learn what I'm going to get across in this video. But it is going to be challenging, and it also very much depends on the last video, video 154. I'll put a link to it up in the upper right corner here. You're going to want to watch that video first, where I show this stuff electronically, both in spreadsheets and also making some graphs in Mathematica, where we observe some interesting things that are kind of unexpected. I want to talk about those things symbolically in this video. Okay, so I'm describing the problem this way. It's from Broverman, the 7th edition. We're deriving the equation that's in the middle of page 398 in chapter 7 of that book. A similar kind of problem is exercise 7.1.4. We're doing annual coupons to keep things simple here. In that exercise, they talk about semi-annual coupons. We're going to derive a formula for the Macaulay duration of an n-year annual coupon bond redeemable at par. And we'll see that this formula turns out to be useful for two things. First of all, finding the limiting value of the Macaulay duration as n goes to infinity. And secondly, and even more subtly, and more importantly for practical applications, seeing what happens to the graph as a function of n when r is less than j, especially when the coupon rate is less than the yield rate, and especially for extra emphasis when they're really far apart. If the coupon rate is a lot less than the yield rate, then the behavior that we're going to talk about here is more extreme. Okay, so let's now look at the given situation. Again, this is deriving the equation in the middle of page 398 of chapter 7. We've got an n-year bond with annual coupons at coupon rate r per year, valued at an effective annual yield rate of j per year. First goal is to show that the Macaulay duration of the bond has this formula, okay? And it's written with this notation, Dmac of j, to say, ordinarily we think of r and n as fixed and j as the variable, and we're interested in what happens to the duration as j changes. But we're more interested actually in this video to think about what happens when r and j are fixed and n is the variable, although technically n is a discrete variable, 1, 2, 3, 4, 5, 6, etc. It's got to be a positive whole number or integer. And we're especially interested in this as the graph of this is a function of n. And again, especially in the case where r minus j would be negative, where r is less than j, so r minus j would be negative, like this thing up here would be negative. Okay, so I want to make some notes before we delve into thinking about this symbolically. I want to note some things. If we got a positive yield rate, so that 1 plus j is bigger than 1, then 1 plus j to the n power is going to go to infinity as n goes to infinity. So this fraction is going to go to 0 in spite of the n up here as n goes to infinity. And the whole duration formula will approach 1 plus j over j, which equals 1 plus 1 over j as n goes to infinity. Okay, we talked about that in video number 154, although I had Mathematica, that computer program, do that for me to verify that. But we can think about it. If we trust this formula is true, then we can just think about it symbolically. That's one benefit of the formula. This expression that we're subtracting goes to 0 as n goes to infinity if the yield rate is positive, as it usually is, and therefore this whole thing approaches this thing right there. Now we get to the subtle part. Also note that if r and j are both positive and r is less than j, then r minus j is negative, so that j minus r is positive, and that means this thing that we're subtracting here, this thing right here, is going to be negative. Why? Well, the bottom's going to be positive, but the top's going to be, I misspoke here, it's going to be negative if n is sufficiently large. Bottom's positive, the top's going to be negative when r is less than j if n is big enough. How big? Well, the top is Negative if and only if, well, the top is negative. The fraction's negative if and only if the top is negative because the bottom is positive. And that's true, solving this inequality for n, if and only if this is true. Now again, we're considering the case where r minus j is negative. I'm subtracting 1 and subtracting j from both sides of this inequality. Then I'm dividing both sides by r minus j, which is negative. That switches the direction of the inequality around. And then I can multiply the top and the bottom by -1 to get this expression, which is a positive quantity here. So again, what I'm saying is this thing that we're subtracting in the formula for the Macaulay duration is negative when n is large enough in the situation where r is less than j. Okay, what does that mean? That if we're subtracting something negative, that means we're really adding something positive. So that means that the graph of the Macaulay duration as a function of n for fixed r and j with r less than j, think about this carefully, eventually goes above its horizontal asymptote. It doesn't just approach it from below, it goes above it before coming back down to it as n continues to increase. So it must have a maximum value. The graph must go up before coming back down. And again, we saw that in video 154, graphically with Mathematica. We also saw that this behavior gets more pronounced or extreme as r and j continue to separate in value with r less than j as they get further and further apart. That maximum gets more pronounced or extreme and also moves to the left. It's for a lower value of n, actually. Okay, so that's pretty interesting. Why is it practically important? Okay, so imagine we're in a situation where the coupon rate is much less than the yield rate. So you get this extreme value behavior in the Macaulay duration that I'm indicating. I'll go ahead and draw a graph. You get something that looks about like this. Okay, so you get this maximum in the Macaulay duration as a function of n. And again, n is a discrete variable, so I should really just graph a bunch of dots there and not connect the dots. But you can say it has a maximum in this situation. What's the practical importance of that? Okay, so when the duration is high, you are subject to something called duration risk. Okay, what does that mean? That means you're more sensitive to changes in the yield rate j. And if you're in a situation where the yield rate is expected to rise, okay, that means your price of your bond is going to go down. And if you're of the mind that you want to resell your bonds, you buy your bond and maybe you hold it to maturity, but maybe you don't. And maybe you are somebody who doesn't typically hold the bond to maturity. So you want to sell it. You don't want the price to be low if you want to sell it, right? You want to get more money. So in a situation where J increases, so the price goes down, long durations are bad, okay? You would want to avoid intermediate values of n that maximize the duration. You'd either want the n to be small or large if you had to. Ideally, you'd want it to be small. If J is expected to increase, you want to avoid large values of n, and more importantly, you want to avoid moderate values of n. You prefer low values. Okay. On the other hand, if J, the yields are expected to go down here in the coming years, then high duration is good. Okay, that's going to cause your price to increase more rapidly than it would for a short duration. You'd want to have a buy a bond with moderate value of n if you expect yield rates to go down in coming years. Okay, so that's the practical importance of all this. Now let's get into the algebraic details. So that this video is not too long. I am going to refer to the formula I wrote down or typed in Mathematica from the last video. It's the equation. So the equation from video number 154, and again that link is in the upper right corner here. And if you want the times where I talk about this equation, it's from time, well, approximately 3.5 minutes in to 6 minutes and 20 seconds in. You'll find the derivation of the formula I'm about to write down. What is that formula? It's the Macaulay duration. It's something kind of similar to this, but it still looks different. I write it as one fraction. I write it as r times 1 plus j to the n plus 1 power minus r times 1 plus j minus nrj plus nj squared all over rj times 1 plus j to the n power minus rj plus j squared. Okay, where does this formula come from? It's not as hard as it looks, actually. Again, I'm able to derive it in about 3 minutes. I use the definition of Macaulay duration. I use the fact that we're talking about an annual bond with these annual coupon rates and yield rates and coupon payments, and use formulas for A and J, the present value of an annuity immediate, a standard one, and IA and J, the present value of an increasing basic annuity immediate, and do some not too hard algebra to write it this way. Okay, so I'm going to use that. Watch this video from this time to see that. Now I want to show that these two things are really the same thing. They don't look that similar. I mean, they're kind of similar, but not exactly similar for sure. Why are they the same? Initially, I tried working with this expression to make it look this way, and it was pretty tricky, okay? It turns out it's easier to start with what you know the answer is, this thing, and show it equals that. Okay, we're going to subtract the fractions. We got to get a common denominator. That's the best way to do this. Now, if you didn't know the answer ahead of time, then it would be really hard, and it would be hard to know what to do with this to even make it look in such a way that you could, it might be useful to be thinking about these two things here. You know, this formula is useful for these notes here. So I don't know. I don't know what to say other than just to say, as far as solving this problem, we'll start with what we know the answer is and get it to this point. Okay? It's especially tricky going back the other way, but we'll do it this way. So let's go ahead and subtract the fractions by getting a common denominator. Okay, so the denominator is going to be the product of j with this whole thing. Let's go ahead and just multiply it all out. So j times r is rj, and that's going to get multiplied by 1 plus j to the n. It'll also get multiplied by -1. So we'll have a minus rj, and then we have j times j is j squared, and there right away we see something good. The denominators match. This matches this. Okay? So that's good. The numerators are not going to immediately match. Okay? We have to do some work with the numerator here to make it ultimately match this thing. But since I'm getting a common denominator, with this fraction I'm multiplying the top and the bottom by this thing. So I got to take now the 1 plus j up here and multiply it by this. I'll just go ahead and write it first. And I think, again, I'll go ahead and multiply the r through here. Like that. And then I have a minus sign, careful, minus sign, and I have this times j. I can go ahead and multiply by j right away, but I think I will use parentheses just for emphasis, just to be careful. So everything gets multiplied by j here. I get a j plus j squared plus, I'll go ahead and multiply that out, nrj, and then minus nj squared. So hopefully this numerator simplifies to this numerator. The tops match. The bottoms already match. The denominators already match. Let's go ahead and multiply this out. I will just keep the denominator the same and not bother rewriting it. So let's see, I got r times 1 plus j to the n times this gives me r times 1 plus j to the n plus 1. That looks good comparing it with this. Then I'd have minus r times 1 plus j will be minus rj, and then I have j times 1 plus j is going to be plus j squared. Distribute the minus sign through, minus j squared minus nrj plus nj squared. Should get some cancellation. Let's see, this j cancels with this j. What else cancels here? I think there's, yep, j squared cancels with this j squared. And these two can combine to give you this thing. And then these two things match these two things here. So we did do it. Let's go ahead and write it out now. We have simplified it down to this. R times 1 plus j to the n plus 1. Again, minus, factor the r out here, r times 1 plus j. Then we have this minus nrj plus nj squared, and again the denominator is the same, rj 1 plus j to the n minus rj plus j squared, and we have a match. This matches this. So that's the algebra of the problem. That's actually doing the problem. But again, I think the note is the most important thing. As far as the practical importance, I'll re-emphasize the things in the note here, and then I'll be done. When we're in the situation where j is positive, so 1 plus j is bigger than 1, 1 plus j to the n will go to infinity as n goes to infinity. This fraction will go to 0 as n goes to infinity, and so the Macaulay duration will approach this thing, which in this graph, that would be where your horizontal asymptote is for fixed j at 1 plus j over j, or if you prefer 1 plus 1 over j. But again, more subtly, and perhaps more importantly, when r is less than j, your coupon rate is less than your yield rate, the graph goes above the horizontal asymptote, perhaps unexpectedly, right? You wouldn't expect that to happen. You might expect it to just always increase toward the horizontal asymptote, but it's got to go above because of this algebra. Ultimately, when n is large enough, bigger than 1 plus j over j minus r, that's where you're going to be above the horizontal asymptote. Right there is approximately at 1 plus j over j minus r, but again, n is a discrete variable here, so it's not necessarily exact. Okay, so again, when interest rates are expected to rise, avoid n's where you're maximizing the duration, but if interest rates are expected to fall, then you do want your durations to be close where this is maximized. But of course, you could also be wrong in your predictions about future interest rates, as people often are. There are certainly some situations where your expectations are probably right, and maybe a lot of people have those same expectations. Thanks for watching.